Hi, and welcome to the Simulation Step-Up series. My name is Yannick Chenio. I'm a simulation specialist with Dassault Systèmes SOLIDWORKS. And in this episode, I will be covering material properties used in SOLIDWORKS simulation, focusing essentially on what's important for linear static analysis. I'll explain all the input properties, where they come from, and what they mean to your final solution. So without further ado, let's get started.
I don't know about you guys, but when I think about material property, the first thing that comes to my mind is how stiff is this material. So when I look at those two spoons here, one is plastic, one is metal. Which one do you think is stiffer? Metal one, right? If I look at those three variations of the same parts, here are three metal rods. It looks like the one in the bottom has more material, so I'd say that's the stiffer one. Pretty obvious so far. If I look at those three metal plates, let's say they're all the same thickness and they're made out of the same material. I'll go with the right one just because of the features on the surface. So as you can see from those examples, we're looking at geometric stiffness, which is due to the shape of the object, and material stiffness. I want to break that into two different categories. So first of all, geometric stiffness. How stiff an object is really depends on its geometry. If you increase the wall thickness, it gets stiffer, or if you add ribs, it gets stiffer, and so on. In finite element analysis, though, the geometric stiffness is represented by the mesh. So make sure you have an adequate mesh to represent your geometry, and the software should account for the proper geometric stiffness. Next is the material stiffness. I'm sure we all understand that the material we use will greatly affect the behavior of our parts. Consider rubber versus granite, for example. Each material has its own physical properties, such as elasticity and density. In finite element analysis, though, the material properties are assigned to the mesh, so using the material properties of the actual part can ensure we get accurate results out of the software. The material properties needed for a static study would be different than the properties needed for a thermal or even for a fatigue study. Conveniently, though, our software helps you identify the important properties for each type of study, and that's the reason for the color coding in the material dialog box. You'll notice that in red we put the properties that are absolutely required. In blue, they may be, depending on some of the effects that we want to account for. And in black are the properties that you definitely don't need for that type of study. The material properties needed in SOLIDWORKS simulation can generally be put into two categories. The properties required to calculate the response, and the properties required to make sense out of the response. The first category will be the input properties, property that you can either access from the material database or type in yourself as a custom material. And the second category will be the failure properties, like yield strength, tensile strength, fatigue strength. Those are used to make sense out of the software solution. In this simulation step-up episode, I will focus only on the input properties needed for a linear static solution. For static structural analysis, SOLIDWORKS simulation provides for inputting the elastic modulus, the Poisson's ratio, the shear modulus, the density, and the coefficient of thermal expansion, or CTE. These are properties you have seen in training or used in the past, but I think it's important to have a good understanding of what they really mean, where they came from, and how they can vary from part to part or material to material. A lot of material property information can be obtained from a stress-strain curve, so let's take a closer look at it to understand its various components. What you see on the screen is a graph of stress on the y-axis versus strain on the x-axis, with three curves plotted on it. The top one is for mild steel, the middle one for cast iron, and notice how it stops more abruptly, and the lower one is for aluminum. Cast iron, the middle curve, in this case qualifies as a brittle material, where the other two are ductile materials. A stress strain curve is obtained from testing a small sample of a given material. More on that test in a few minutes. And where you see those curves end on the right is actually where the material breaks. The maximum stress a given material can handle before breaking is called the ultimate strength, and I'll show it in blue on the graph for the respective materials. The point where the material stops being elastic is called the yield strength, and I'm showing it in red here. For ductile material like steel, the yield is very obvious as it corresponds to a sudden break in the curve and a small dip before the curve starts going up again. In some cases, however, like you can see in the aluminum curve, there's no sudden break in the curve. So as a common substitute for the yield strength, we can use the 0.2% proof strength, which corresponds to the stress level that will result in 0.2% of residual strain after all loads are completely removed. In general, at the yield point, you have a factor of safety of 1. If you exceed yield, your factor of safety drops below 1. Finally, you notice that stress-strain curve as a straight line at the beginning. The slope of that initial portion of the curve is your elastic modulus, or also known as the Young's modulus. In the absence of a straight portion of the stress-strain curve, which is often the case with plastics material, we'll use the first 2 data points from the tensile test to generate the slope. Next, I'll be talking about the tensile test itself that is used to obtain the stress-strain curve. But before I advance the slide, note that the slope or elastic modulus can vary greatly from material to material. The standard tensile test for metals is the ASTM E8 tensile test. It uses a round sample that is mounted to a rigid base on one end and connected to an actuator on the other end. The machine will then stretch the part and measure the force required along the way. Here's an accelerated version of that test. First, you notice the strain gauges connect to the sample. And then we'll look at the computer screen and we'll basically start stretching that part vertically along the axis. You'll notice the straight portion of the curve, the dip, and then as we keep pulling, take a closer look at the image. It's pretty obvious right now. You'll notice that the material is stretching and the force required goes up, but all of a sudden, the force levels out. And when it starts going back down again, this is when the necks start forming. It's the onside of fracture. And all of a sudden, bang, the part breaks. So we get a force versus deflection plot out of the tensile test, but it will look exactly the same as the engineering stress-strain curve, because the engineering stress is simply force divided by the original cross-sectional area, which is a constant, and the engineering strain is simply the elongation divided by the original length, which is also a constant. All that makes the engineering stress-strain curve look the same as the curve we had earlier. So if you were to use the true stress-strain curve, though, which uses the Poisson's ratio in the elastic portion of the model to account for the exact cross-section at that given moment, the curve would look significantly different, especially past the yield point once the neck starts forming. For plastic materials, a different spec, ASTM D638, is required to determine the tensile property for stress-strain curve. And unlike the metal test, the sample used for plastics are flat or dog bone shaped, where they are thinner in the middle and much wider on the ends to hold apart. Because plastics are inherently very nonlinear, where they start to deviate from the linear almost immediately, the elastic modulus is typically defined as the initial slope between the first couple data points in the test. So the Young's modulus is only applicable for a very small amount of strain, so that needs to be taken into account if you are going to use plastics material for linear static analysis in SOLIDWORKS simulation. At larger strain, you will start seeing noticeable differences between software results and actual tests, and you need to be aware of that. More specifically, regarding the Young's modulus, it is represented by the letter E, and as I said before, is the slope of the linear portion of the stress-strain curve. For steels, the slope is always linear up to the yield strength of the material, but for other material, that's not always necessarily so true. Remember that the tensile tests represent the strength of the material in tension. Many materials are symmetric, meaning that their tensile properties are the same as their compressive properties. But that's not always true, especially if you're dealing with brittle materials. So if you're in this situation, you might want to consider a more advanced material model available in SOLIDWORKS Simulation Premium to predict the behavior accurately. How does Young's modulus vary in engineering practice? Typically, with steels And with other engineering metals, the Young's modulus will remain consistent across varying alloys. For steel, the Young's modulus will be around 30 million psi or 200,000 megapascals. Whether for aluminum, it's usually around 10 million psi or 65,000 megapascals. Various alloy will come and go, but the stiffness of those alloys is going to be consistent. What will be different is the failure characteristics of those materials, so that's what you should be paying attention to if you think using a stronger steel will improve a dangerous stress situation. Remember though, this is not necessarily true for other materials, particularly plastics, where the Young's modulus can vary greatly based on the molding process. Also, the Young's modulus, especially for plastics and polymer, can be extremely sensitive to changes in temperature or strain rate. By strain rate, I mean the speed at which the part is being loaded. At lower temperature, plastics tend to behave more stiffly, and at higher strain rates, the plastics tend to behave more stiffly as well. That characteristic is true for engineering metals as well, but variation is not nearly as obvious as it is for plastics. And if your application involves making your parts work in temperatures other than room temperature, you might want to consider entering the temperature dependence of your material property in the material database. How does varying the Young's modulus affect your FEA results? Well, remember that the Young's modulus represents the stiffness of your material. As an analogy, if you consider your part to be a spring mass system that behaves according to Hooke's law, so F equal kx, then your Young's modulus is the spring constant k. Consequently, you can say that deflection varies linearly with Young's modulus. So for the same geometry and the same loading scenario, an aluminum part will deflect more than a steel part by a factor of 3, since the Young's modulus of aluminum is 3 times less than the one of steel. As for the stress, it will be exactly the same regardless of the material. This is sometimes a statement that's hard to believe. This is because stress is independent of Young's modulus. To help you understand that better, these are some of the basic equations for basic stress test in engineering structural analysis. So for uniaxial tension of a rod, the stress is simply the force over the area. For pure bending of a plate, the stress is the moment times the outer fiber distance divided by the cross-sectional moment of inertia. Notice that in none of those equations do you find Young's modulus or any other material properties term, because stress is independent of your material properties. It doesn't mean failure is independent of material property, but stress is. Let's take a look at a side-by-side comparison of two materials to illustrate what we just discussed. Steel has a Young's modulus of 30 million psi, which is 3 times stiffer than the aluminum at 10 million psi. So for a given geometry and a given load, an aluminum part will deflect 3 times more than the steel part. And as for the stress, it will be exactly the same regardless of the material. So consider this if you're thinking about using a different material to alleviate stress in your design. Poisson's ratio is another one of the input properties for static analysis and is essentially the ratio of lateral strain to longitudinal strain. As you can see on the exaggerated animation on the right, when a bar is loaded in pure tension, you do see the cross-section or lateral dimension reduced by a factor related to the Poisson's ratio. You notice that a load is applied in one direction, but it couples the deformation in the other two directions. Values for Poisson's ratio for all the material that exists out there are always between 0 and just under 0.5. As this number would result in numerical singularity. So realistically, Poisson's ratio is in the range 0 to 0.499 in the linear elastic portion of the material curve. I'm pretty sure you've all seen the effect of the Poisson's ratio in your analysis. Just fix a block on one end and pull on the opposite hand. The high stress at the restraint are due to the Poisson's ratio and the fact that the material is not allowed to shrink in the lateral direction due to the artificial condition on the face. Stress there should be ignored, or a more appropriate set of constraints should be used to eliminate this anomaly. For steel, Poisson's ratio is usually 0.3, and it's a good number to use if you don't have a Poisson's ratio for your materials. If you forget to enter the Poisson's ratio, note that the software, SOLIDWORKS Simulation, will warn you that a value of 0 will be used. Now, how big of an impact would this have on your results? To find out, we ran 5 cases where the only variable was the Poisson's ratio. The results showed that the displacement and von Mises stress vary by only 4%. So we can conclude that Poisson's ratio has only a small impact on the overall solution, certainly well within the error introduced by local mesh problems. If on top of this, you account for the fact that Poisson's ratio for the vast majority of materials out there is between 0.2 and 0.4, and if you use 0.3 as your default guess, the potential error you're introducing would be 2% at most. Shear modulus is another one of the input properties for static analysis and is linearly related to the Young's modulus and the Poisson's ratio by the equation you see on the screen. Since you can calculate the third property using the other two, the shear modulus is pretty much redundant. Density is only required if you're performing either frequency analysis or if you're doing a static analysis and are specifying either gravity, acceleration, or centrifugal load in your model. Because those are acceleration load and they need a mass to act on, so density is the way mass gets calculated. By definition, mass density is the ratio of mass to volume. However, in English units, the weight density is more common and differs from the mass density by the gravitational constant. If you're creating your own custom material and unsure of the units for density of your material, build a 1-inch cube, fix it at the top and assign gravity, and query the reaction force at the location of the restraint. That force should equal the weight of the part, and use this as a sanity check to make sure that your densities enter correctly. The coefficient of thermal expansion, also known as CTE, is the last input property we'll cover today. It indicates how much a material expands and contracts when subjected to a temperature change. This property is only required in a linear static analysis if you're going to evaluate stresses and deformation due to thermal expansion. Typically, the setup would require one to apply a thermal load, but not a thermal load to calculate temperatures, but rather a thermal load to determine stresses and deflection relative to a baseline, which typically corresponds to ambient temperature. This material property can be found in a number of resources and can make a pretty significant difference in your results. So if you're going to solve this type of problems pretty regularly, we do recommend you look for the coefficient of thermal expansion specific to your material instead of using the one from the database, which could be considered a little more averaged. And this chapter would not be complete without a closer look at the difference between an isotropic and an orthotropic material. The standard default material in SOLIDWORKS simulation is isotropic. It means that all the properties are basically the same in all directions. Many materials don't behave that way though, and they fall in the orthotropic or maybe sometimes anisotropic category. Wood is a perfect example of an orthotropic material as the grain affects its behavior and strength. Also, I wanted to point out that if you're looking to find properties for a specific material, you can use our materiality library, which is accessible from a hyperlink at the bottom of the material dialog box. It's a pretty extensive online material library that's only for simulation professional and simulation premium users that are on subscription, and it contains thousands and thousands of certified materials from reliable sources. As a matter of fact, you can check the data certificates. And the nice thing is you can really filter by study type and also material type, whether it's a plastic, a rubber, or type of metal. In the simulation step-up episode, we basically explored the input properties required for linear structural analysis in SOLIDWORKS simulation. We reviewed the basic test method for tensile testing, and we also discussed the impact of property variation on your analysis results. If you want to know more on the subject of material in analysis, I would like to recommend you to contact your SOLIDWORKS reseller and maybe consider an in-depth training on the subject to become a real expert. You can also review the online help for a more detailed description of all the features I discussed today. And also I want to point out a few more databases that are very useful if you're trying to locate a specific material. MathWeb is one of them, but you also see the item at the bottom here. Other resources, some are great for plastic materials as well, so feel free to check those out, and we'll catch you soon.
I hope you enjoyed this session, part of the SOLIDWORKS Simulation Step Up series. Join us next time for more episodes on how to best use our simulation tools.